Well, hello, class.
Hello. Hello.
Hello. Hello.
Well, we're going to look at today extrema of functions of two variables, and what we're talking about is something that you might remember from Calculus 1 when you looked at how do you find relative maximums and minimums, or even absolute maximums and minimums if you're given in Calc 1 if you're given an interval, and in Calc 2 if you're given a domain set. So we'll begin a discussion with what does it mean to be absolute or relative extrema. And the idea is, if we can find a number that the function never gets bigger than, then that would be a maximum value for a function. And if we find a number that the function never gets smaller than, that would be a minimum value for the function. And so what do you mean by maximum and minimum? And you have to think about the function being defined on a closed, then what that means is it contains all its boundary points. And it's bounded, which means it has an upper bound and it has a lower bound. And so usually when you say on a closed region, that means it'll be on a closed disk. Anyway, if it has values f of AB and f of CD such that f of AB is less than or equal to f of xy, which is less than or equal to f of CD, for all x in that region R, which is a subset of R squared, so you could call it a disk, then f of A and f of B are the minimum and maximum values of the function in the region R, okay? And that would make them absolute extrema. So here's the extreme value theorem. Let f be a continuous function of two variables, x and y, defined on a closed and bounded region R in the xy plane. You understand the problems. If the region does not contain its boundary, then it's going to be hard to find a number f of AB that's less than or equal to f of xy, less than or equal to f of CD. So there's at least one point in the region R where f takes on its minimum value, and at least one point in the region R where f takes on its maximum value. That's kind of intuitive. So some books use the terminology absolute minimum and absolute maximum, and they can be different from relative extrema, which would be relative minimum and relative maximum. If you think about a cubic function, let me draw one for you here and say this is our cubic function. F of x is defined to be x cubed minus 7x plus 6. I think this would be a good example. And if I wanted to draw a graph of this cubic function, then I would just simply draw for this particular x and this particular this isn't the best picture, but I'm going to work on it until it is. I want properties on the format. I want to change it to crossed, and I want to change, oh, these numbers are crazy. So let's just go from -10 to 10. And now you should see, I think fairly clearly, that for instance this is a relative minimum, but there is no absolute minimum because the function keeps getting smaller. And it looks like if I went just a little bit higher than 10, maybe 15, you should see that there's a relative maximum here, but there is no absolute maximum because the function just keeps getting huger as you keep going, right? And so that terminology, relative extrema, the relative extrema are this point and this point, and the absolute extrema really kind of don't exist, or they're infinity and negative infinity, if you want to call it that. Okay, so relative extrema. Let f be a function defined on a region R containing the point x sub 0, y sub 0. The function f has a relative minimum at x sub 0, y sub 0 if f of x sub 0, y sub 0 is less than or equal to f of xy for all xy in an open disk containing x sub 0, y sub 0. And it just means there is somewhere an open disk that contains values that are always bigger than that also contains this. Open disk is what you would say instead of open interval. Open interval would be for a function of one variable. So the function f has a relative maximum. Well, you could probably figure that one. As long as there's an open disk containing this, such that there's a, that f of xy in the disk is always less than or equal to f of x sub 0, y sub 0. So we can look at a picture of relative extrema in this function. F of xy equals sine of y plus sine of x. And of course that's just a wiggly thing, but you can see the white tops of the peaks are all relative maximums, and the bottoms, the blue, are all look like the lakes down there in between. Those are all relative minimums. And so, I mean, we could mess with this and make it look a little different. We could say times 2, and I don't know what that would do. It just would make it a little bit peakier in one direction than the other, but and we could play with this a lot. We could say instead of sine of x, we could say sine of 2 times x, right? Which makes it wigglier in one direction than in the other direction. Or we could say sine of x over 2, which makes it only half as wiggly in one direction. So, but still you can see the peaks and the valleys, I think, quite clearly. And so what we're looking at is relative maximums here, 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 and here, and relative minimums here, 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 and here. And of course that's not the entire domain, but if you could imagine in the xy plane there's an open disk containing this peak point, right, well, there's an open disk actually in the xy plane such that the peak point is bigger than f of xy in all the other points in that disk. And same way with the minimum, there's an open disk that contains the place where the valley is deepest, so to speak. And so on any place where you'd pick in that disk except for the bottom spot, it would be bigger than f evaluated at the bottom spot. Guess that was easy enough.